Hello everybody. What we're going to do today is talk a little bit about closure. In order to do that, we're going to dive into some things like implications and their implications. Yeah. So when we say that a set is closed under some operation, what we mean is when you apply that operation to elements in the set, you always end up back in the set. And so I like to make up some toy finite examples in order to start off this discussion. And so we're going to start with this set right here. Now, each element of this set has three pieces, a top, a middle, and a bottom. And so you can invent a bunch of operators on this set. You might say that adding two elements of the set, maybe that swaps their tops. Now, if you do that, if you swap the tops of these things, you end up with elements back in this set. So you might say that the top swap or the addition operation is closed for this shapes set. What's really cool about that is that you can prove these things exhaustively. That's why we're using this finite set here. And you can say things like, no matter what, I can show you that if you swap the tops of any two of these things, you end up with elements back in the set. You might ask other questions about this set and be able to prove or disprove them in that way. So you might say, hey, if I change the middle of an element of this set to a circle, maybe you call that the middle circle operation, do I end up with elements in the set? And we can exhaustively try this to prove it, right? So if I do circle, circle, triangle, well, that's in the set. If I do circle, circle, rectangle, well, that's in the set. If I do circle, circle, rectangle, that's in the set. Circle, circle, triangle, that's in the set. And then, of course, changing these to circles ends up being the identity operation for those two. So I end up back in the set. So you might say, hey, changing the middle to a circle leads us to elements that are back in the set. So this set is closed under the middle circle operation. Now, if you try to do the same circle operation to the bottom, it's very clear that that doesn't work for any element in the set. And you can prove that with one counterexample. So what I'm going to do is I'm going to lead you through a bunch of these types of questions. Briefly, I'll show you the questions for this set and let you kind of work on them a little bit. And then there's another video where we kind of do some of that for integers and things like that. So I'll let you use that video for those. I'm not going to spend a lot of time on this part because we have a lot to get through in this video and time will run away from us. So go ahead and pause and try some of these. So this is the swap top operation. We decided that was closed. How about if you swap any bottoms? Do you end up with an element in the set? Go ahead and pause, think about this, see if you can prove it. I think that one is also closed. What if I change the bottom to a triangle? So let's look at the set real quick. Go ahead and pause. If you change the bottom to a triangle, where do you end up? Okay, well, that should be closed as well. How about if you change the bottom to a rectangle or a circle? I'll come back up here and then you can pause. Right? We did one of those already. Anyway, we'll move on. There's lots of other things, and we asked, how do you prove these? And the answer is you can prove them exhaustively by just trying everything. Now, things get more interesting when you move into infinite sets. So one of the simple infinite sets that you already have some feelings about are things like the counting numbers, the natural numbers, integers, things like that are things that you're used to using in mathematics, and so you can talk about closure with them pretty easy. So let's ask ourselves, are these sets closed under certain operations? How about under addition? If I take two natural numbers and I add them together, do I end up with another natural number? The answer is yes. So, if I take a positive integer and I add it to another positive integer, I end up with a positive integer. So we would say, yes, they're closed under addition. All right, let's try subtraction. Go ahead and pause and think about this for a second. Are natural numbers closed under subtraction? Now, hopefully you're back. If the answer is no, then you only need to show this for one possible counterexample. So for example, if you do 1 minus 2, that is one counterexample, and that means that the natural numbers are not closed under subtraction. Some subtractions work. 3 minus 2 does lead you back to the natural numbers, but because there's at least one that doesn't work, you would say the natural numbers are not closed under subtraction. How about multiplication? Turns out multiplication works out okay. How about division? Go ahead and pause and think about this. Turns out division's not okay. If I do 1 divided by 2, I end up as a counterexample, so natural numbers are not closed under division. Because there is some elements that I take out of the set, and when I apply them, I end up with an element outside of the set. this applies to us in coding because a lot of times our numerical systems in coding are forced to be closed in weird ways, and we have to be aware that that doesn't follow normal mathematics. But again, we're going to push on the theory side of things rather than the fully applied side in these videos. How about negation? If I negate something, turns out that never works for the natural numbers, right? -1, -2, -3. So negation is kind of the opposite of closure. You know, it never works, which is kind of interesting. You can try a bunch of other operations, like reciprocals of numbers, which sometimes works, but usually doesn't. Exponentiation, factorials, you know, pick some operations, modulus, they're all cool, and they all have different answers. You can also try integers and real numbers and see how all these things work there. I do touch on integers a little bit in another video, so I'm not going to do these here. I'll leave these as an exercise for you. Okay, all right. So, why is this useful to know for us? Again, type safety as a developer, but in our case, we're going to use them for proofs. And so I think I'll chop this into 2 videos, and I'll leave this as kind of an introduction to closure. And then in the next video, I'll talk about closure as a proof mechanism. All right, see you next time. As usual, be kind to each other. And in order to do that, you have to be kind to yourself first. See you next time. Bye.